Look at question 6. It says find the limit of the sequence if it converges or explain why it diverges. All right, so for part A, looking at the sequence a sub n, which is equal to the product of 3 minus 1 over 2 to the n and 2 plus 1 over 2 to the n. Okay, so the idea here is to just look at what's happening at each individual term and then put it all together for the limit. Okay, so here, as we let n approach infinity, 2 to the n is going to approach infinity, and so 1 over 2 to the n will approach 0. Okay, so a sub n then will approach the product of 3 minus 0 and 2 plus 0, and that's just equal to 6. Okay, so here we say that the limit as n approaches infinity of a sub n is equal to 6, and the sequence converges. All right, now for part B, we have b sub n is equal to sine squared of n divided by n. Okay, so the rough idea here is that the numerator sine squared of n is going to be a value between 0 and 1, and the denominator n is going to become infinitely large. And so if I take numbers between 0 and 1 and divide them by something infinitely large, the result's going to be something infinitely small. So the limit should be 0, and that is exactly the case. So here's what I'm noting here. The intuitive approach here is to say, well, you know, some number between 0 and 1, so 1 for the maximum value, divided by something infinitely big, that's going to give you something infinitely small. Okay, so now to make this a bit more precise, we can use what's called the Squeeze Theorem, which would have been something you saw in Calc 1, maybe a little bit in Calc 2. I'm going to remind you of what it says here. Okay, so now sine squared of n divided by n, it's certainly non-negative, so it's bounded below by 0. And then what I'm saying up here is that since sine squared of n is always between 0 and 1, this ratio will always be bounded above by 1 over n. Okay, and 1 over n, this thing on the right, is going to 0 as we let n approach infinity. And so since sine squared of n over n is squeezed between 0 and something approaching 0, this thing then likewise will have to approach 0 by the Squeeze Theorem. Okay, so here the limit as n approaches infinity of b sub n is equal to 0, and again we say the sequence converges. Alright, now for part C, we got c sub n is equal to n plus negative 1 to the n minus first power, all divided by n. Alright, so here my recommendation is to first rewrite this expression. I'm doing a bit of algebra, so if I divide n by itself, this is a 1, and then here I have a negative 1 to the n minus first power divided by n. So now what happens to this term as we let n become infinitely large? Well, in much the same light as part B, it's going to approach 0. Why? Well, the numerator is just going to be either a 1 or a negative 1, and we're dividing it by, well, something approaching infinity. Okay, now to make it a bit more precise using the Squeeze Theorem, okay, I'm just saying, okay, this term will be bounded below by negative 1 over n, and it'll be bounded above by 1 over n. And since 1 over n approaches 0, right, both of these things on the left and the right approach 0, so negative 1 to the n minus first, all divided by n, must approach 0 as well. So that all implies then that c sub n will approach 1 plus 0, which is just equal to 1, and so c sub n converges to 1. All right, very good. Let's next turn to parts D and E here. We got for D, the sequence d sub n, which is natural log of n minus the natural log of n plus 1. Okay, so here, as we let n approach infinity, recall that the natural log of n, sorry there, take it off the eraser, there it goes. Natural log of n blows up to infinity, and the natural log of n plus 1 also will approach infinity, and I'm taking the difference between these two terms. So it's not exactly clear what's going to happen in the limit, right? Do they approach infinity at comparable rates, so this difference will be 0 in the limit? Maybe, but maybe this natural log of n plus 1 term approaches infinity sufficiently faster than this thing, and so this might carry it to some other value. Well, what can we do? Well, a useful thing here is to use logarithm properties. Okay, so I'm going to rewrite the expression using log properties. This is a difference of logarithms, so I can write that as the natural log of n over n plus 1. And so now if I divide n in the numerator and n plus 1 in the denominator both by n, I'm just going to, in other words, rewrite the inside of the natural log as 1 over 1 plus 1 over n. And see, as n approaches infinity, 1 over n goes to 0. And so that says the sequence d sub n will approach the natural log of 1 over 1 plus 0, which is just the natural log of 1, and the natural log of 1 is 0. And so here, the sequence d sub n converges to 0. All right. How about part E? You got e sub n, which is equal to the product of n and sine of 1 over n. Now here, this first factor n, this thing is approaching infinity, whereas the second factor, sine of 1 over n, this is going to approach the sine of, well, 0. And the sine of 0 is equal to 0. Okay? So this is what's known as an infinity times 0 indeterminate form. Okay? So with something blowing up times something becoming infinitely small, it's not clear what's going to happen in the limit. It has to do with the rates at which this thing gets big and this thing gets small. Okay, so the idea here is to use L'Hopital's rule. Okay, so I'm going to first rewrite this expression as the sine of 1 over n divided by 1 over n. Okay, and then here I'm just noting that the numerator, which is the sine of 1 over n, it approaches the sine of 0, which is 0. And 1 over n, that also is approaching 0. So this is what's called a 0 over 0 indeterminate form. Okay, so we can use L'Hopital's rule, which is a reminder here. It says that if you have two nice differentiable functions, and let's say they both approach 0 as we let n approach infinity, then the limit of their ratio is equal to the limit of the ratio of their derivatives. Okay, so to apply that here, okay, I'm going to differentiate the numerator and I'm going to differentiate the denominator separately, and then I'm going to take the limit of the ratio of those derivatives. So that looks like this. We got the cosine, because it's the derivative of sine, of 1 over n, and then from the chain rule, we have to multiply by the derivative of 1 over n, and that's negative 1 over n squared. And notice I put just the little LR here to emphasize the fact that we're applying L'Hopital's rule in this step. Now in the denominator, if I differentiate 1 over n, I get, well, again, negative 1 over n squared. Okay, so now looking at that, that is great, because you notice the negative 1 over n squareds just divide out to 1. And so I'm left with taking the limit as n approaches infinity of the cosine of 1 over n, and that's just equal to the cosine of 0. And the cosine of 0 is equal to 1, and so here we conclude that the sequence e sub n converges to 1, which, as I noted at the beginning, that's not really all that apparent, just given the fact that this factor is blowing up and this factor is becoming infinitely small. There's a certain balancing act that takes place, and the product actually has a limit of 1. All right, cool. So now let's press on to the next two, f and g. These involve factorials. Okay, so for f, we have f sub n is equal to the ratio 4 to the n all divided by n factorial. And so this numerator here is blowing up. So it's going to approach infinity, right? 4 to the n becomes infinitely large. N factorial is also going to approach infinity. Okay, so now what's going to happen for the ratio? Okay, you might say, well, could we maybe do like a L'Hopital's rule kind of thing? You're going to run into a problem there because of the n factorial. Okay, so here, what I recommend doing, just at least to start, let's just play around with a calculator and plug in a couple different values for n. Okay, so let's say, n is 8. This is like, 1.62. If I increase that to say n is 12, I'll get a little bit smaller. Oh, looks like as I let n get large, this thing is getting really, really small. And if I go out to say n equals 50, this is 10 to the negative 35th power. Yeah, that strongly suggests that this ratio here approaches 0. Okay. And so, okay, what do we do in that case? Is that enough? Well, no. While it strongly suggests that the ratio will approach 0, we need to actually construct a mathematical argument to prove why it approaches 0. Okay, so to do that, I'm going to start by just writing this ratio in expanded form. Okay, so 4 to the n, this is, well, just 4 times itself, n times. Okay, so 4 times 4 times 4, all the way up until we get to our nth 4. And I've just included all these intermediate factors just to emphasize the next couple of steps to illustrate what's going on. So downstairs we have n factorials. This is 1 times 2 times 3, all the way up until we get to n. Again, I've just included these intermediate factors to illustrate the next couple of steps. Okay, so now what am I going to do with this? Well, for these first 4 terms, okay, in the numerator and denominator, their ratio, okay, is just a number. It's, in this case, 32 thirds. Okay, but then notice once I get to this term, 4/5, then 4/6, 4/7, so on and so forth, all of these ratios are numbers that are less than 1. Okay, so I have some finite number, 32 thirds. Then I'm multiplying a whole bunch of things that are all smaller than 1. And then I'm just going to leave off, I have this little 4 over n for my last factor, which will be, in general, really small if n is really big. Okay, so why exactly am I doing this? Well, the hope here is that, again, we sense that this thing approaches 0. So if I can show that this thing is always smaller than something that's getting really small, then this thing itself must also approach 0. All right, so that's exactly what we do here. All right, now from this grouping here, we can say that 4 to the n over n factorial, it's going to be bounded above. So in other words, less than or equal to 32 thirds. That's just this chunk. And then here I'm just replacing each one of these ratios by 1. Okay? And so again, since each one of these is less than 1, notice this is not an equality, but a less than or equal to inequality. And we're saying this thing is smaller than this, where I've just replaced these with a bunch of 1s. And then I still have my 4 over n. Now this thing on the right is equal to 128 divided by 3n. And what happens to it as n gets infinitely big? Well, it's going to approach 0. Okay, so now we can go ahead and finish by just using the squeeze theorem. Okay, 128 over 3n, right? That thing approaches 0 as we let n approach infinity. And since 4 to the n over n factorial is squeezed between 0 and something becoming infinitely small, it will approach 0 by the squeeze theorem. Okay, so the sequence f sub n here does approach 0 and it converges. All right, cool. So how about part G? We got G sub n is negative 1 to the n times n plus 2 factorial, all divided by n factorial. Well, here with factorials that are being divided like this, let's write this out in expanded form first and note that there's going to be a whole bunch of nice cancellation. So n plus 2 factorial, that's 1 times 2 times 3 all the way up until we get to n plus 2. Notice I've included the n and the n plus 1 there just to emphasize what's going on in the next few steps. Downstairs we got n factorial, so that's 1 times 2 times 3 up until we get to n. Alright, so now these, the 1 times 2 times 3 up to n, those are going to divide out, which is great. And this leaves us with negative 1 to the n times n plus 1 times n plus 2. Now what happens there? Well, as n gets big, this negative 1 to the n is just going to alternate the sign from positive to negative, so on and so forth. The n plus 1 times n plus 2, that's going to blow up. It's going to become infinitely large. And so if you were to graph this sequence, you'd see something like this. Okay, the sign is going to alternate, and the magnitude of each successive term will grow, and in fact the magnitude will approach infinity. So this sequence does not approach one specific value as we let n approach infinity. So here the limit does not exist, and there we say that the sequence diverges. Alright, cool. And now for the very last one here, we got part H. Sorry, I need to get rid of these. For part H, we're looking at the sequence h sub n, which is the inverse tangent, or also known as the arctangent of n over 2. And the key thing to remember here from Calc 2 is that the graph of the arctangent function looks like this. Okay, so recall you take the principal branch of the tangent function from minus pi over 2 to pi over 2, and, well, you find its inverse. So in other words, you graphically reflect it about the line y equals x, and you get this S-shaped looking graph, that's known as a sigmoidal graph, and it has two horizontal asymptotes, okay? Pi over 2 is you move way out to the right, and negative pi over 2 is you move way out to the left. The key thing for us is that the inverse tangent of, well, something will approach pi over 2 if that something is becoming infinitely big. This is really just saying as you move way out to the right on this graph, okay, the arctangent output will approach pi over 2. Okay, so that makes this problem pretty darn simple, because as n approaches infinity, n over 2 will approach infinity. And by what I'm saying here, that means that the arctangent will approach pi over 2. Okay, so the sequence h sub n converges to pi over 2. Great. Well, all right, that's going to do it for this video. There's a lot packed in here, so you may want to rewatch some of these. Certainly let me know if you have questions about any of them. But that's going to do it, and I'll see you in the next video. Thanks so much.